Great. All right. Well, thanks for the very nice introduction, Jennifer, and thank everyone for coming and taking time out of your day to watch me present how to accelerate your science with on-demand processing from ASF. So first, I'll give a little background on what ASF is. The NASA Alaska Satellite Facility Distributed Active Archives, or ASF DAAC, is one of 12 Earth Observing System Data and Information System, or OSDIS DAACs, that manage, archive, and distribute Earth science data as part of NASA's Earth Science Data Systems program. Here at ASF DAAC, we operate the NASA Archive of Synthetic Aperture Radar, or SAR, data for a variety of satellites and aircrafts, providing these data and associated specialty services to a diverse community worldwide. In addition to NASA data, we host and archive data from the European, Japanese, and Canadian space agencies. All of our data is easy to access and free to use, or at least we try to make it easy to access, and if it's not, let us know. In addition, we also have some other capabilities at ASF DAAC. We do satellite tracking, and we have ground station capabilities. We do a lot of SAR and remote sensing training and education, and we provide some level of science support via our chief scientists, typically as collaborative grant applications and support. And my focus on ASF is in very much the science support space. So why synthetic aperture radar data, or why SAR data? SAR is an active microwave imaging system. So by being active, it means that we're sending out a pulse. That pulse is bouncing off of something and coming back. So we can do it night or day. We're not waiting, or we're not reliant on the sun's illumination. If we know the pulse we're sending out, we get back not only the amplitude or the strength of that pulse, but also the phase or timing of the pulse, how long it took to bounce and come back. And because it's microwave, we can penetrate clouds or dust. So this is a really strong platform for Earth observing because it's active all the time, day or night, and it doesn't depend on the weather. It's also suitable for interferometry, and that's kind of a big word, so I'm going to go over what is interferometric SAR real quick. Basically, what you're doing in interferometric SAR is you're taking two SAR acquisitions over the same area. They're either separated by time or space, and you're measuring the phase, the two-way travel time of those acquisitions. And then you take those two and you difference them, which is what we call an interferogram. We difference the phase. And if you have the images in two different positions, you can use that to decide where the ground is in addition to the satellite. So you can do mapping of kind of the terrain surface, or if you have the passes over, or the acquisitions at two different times, you can see how the ground has changed if you know what the ground should have looked like. So our main data set at ASF is Sentinel-1. It's a repeat pass interferometry, so it's two acquisitions at a different time. And that means it's best for deformational mapping. We're looking at kind of how the ground changed over time, our satellite. When those acquisitions happen, the satellite's in slightly different positions. We call that the perpendicular baseline. And there was a different time in the acquisition, so that's the temporal baseline. To get really good SAR measurements, you typically want to have a very small perpendicular baseline, and you can lose coherence or the ability to look at the phase if you separate the temporal baseline too much. And so Vertex, our primary search interface, which I'll demonstrate later, has two tools to kind of help you pick really good InSAR or pairs for InSAR processing. The baseline tool that helps you pick specific pairs, so you can really dial in the perpendicular baseline and the temporal baseline to pick a really nice pair for interferometry. And we also have the SBAS, or the short baseline subset, that helps you pick an InSAR pair stack, so a whole bunch of pairs over time, so you can do time series analysis of kind of changes throughout time. So it being suitable for interferometry means that this is a robust platform for event and change monitoring. Some examples might be how volcanoes change, what happens after earthquakes, and watching glacial movement. So Sentinel-1, our primary thing primary set that I talked about, is a European Space Agency mission. There's 2 polar orbiting satellites, Sentinel A and B, and each satellite covers the globe every 12 days. So at any spot on the globe, there's a 12-day repeat cycle of reacquisition of this. So that means you can get pairs for InSAR every 12 days. But because these satellites are offset by 180 degrees, there's a potential for a 6-day repeat in acquisition. So Sentinel A may come over, and 6 days later, Sentinel B will come over. We have global coverage because of the polar fit, and it's C-band microwave imaging. So when new data is acquired, there's a guarantee that no more than 3 days after acquisition, it'll be available. ESA publishes it at least 3 or less than 3 days. Typically, they're really good and get it out in less than 24 hours. And then once they get it out, we ingest and archive it, and it's available from us. It's free and easy to download from ASF in multiple formats. I'll talk about those in a second. And you can then process the data to kind of analysis-ready data. And what I mean by that is Sentinel-1 data comes in 2 primary level 1 products is the terminology, but basically they're taking the raw data from the satellite and processing them a little bit into an SLC, which is a single looked complex product. So it's in the slant range geometry, the geometry of the satellite pointing down. It's not very GIS friendly because it's not referenced to the ground. There's multiple images in the product package, which is a zip archive for each of the swaths that the satellite recorded. What's important about SLCs is that they include the phase data, which is required for generating interferograms, but they're a little harder to use directly for applications because they're not GIS friendly. There's also a GRD product, or a ground range detected product, that's actually multi-looked and projected to ground range, so it's easy to view in GIS applications, and it's been processed so that there's square pixels and there's small file sizes. So if you're just looking for amplitude data, GRDs are a great product, but the phase data is lost in that processing, so you cannot generate interferograms. So you'll want to always grab SLCs for interferograms. So why this on-demand service that I'm presenting? And the main reasons are processing SAR data is complex. The data is complex, as I just described. The processing to change the data into something that's corrected, whether doing metric terrain correction or doing the interferograms, are complex to use, often require specialized software, and that software is resource intensive. Compute and memory is what I'm talking about here. And then on top of that, kind of just the step of going through producing one interferogram is kind of hard. The sheer volume of data available is rather large. Sentinel-1 has produced over 10 petabytes of data since the start of its mission in 2014. And so a small area of interest may still result in many thousands of scenes, especially if you're looking back in time. So what we're trying to provide is skipping the processing step for you. You just go straight to your science applications, come to Vertex, search for your products, and say, I want interferograms, I want radiometric terrain corrected products. You can focus on your science and applications. Let us process everything in parallel in the cloud. That was a super fast introduction to SAR. So I'm going to point to some other resources. There has been 3 good similar webinars that Heidi Christensen, one of our panelists, has presented, and has done a good job of doing a more detailed description of SAR and especially RTC processing. Our chief scientist, Franz Meyer, has a edX Alaska course coming up on September 7th. That covers synthetic aperture radar in a hazards application. That course is, you can take it, you can go through the whole thing for free. If you want a verified certificate, it costs $199 US. There's also 2 really good open access books that are available for. There's the SAR handbook published in 2019, and it's focused on forest monitoring and biomass estimation, but does a very good job of giving the high-level background of SAR and how to work with SAR data. If you want a really detailed graduate level dive into SAR data, polarimetric synthetic aperture radar principles and applications was published earlier this year. And it's also open access, and it has great examples of forest, agriculture, cryosphere, and urban and ocean domain kind of use case examples. So recommend checking those out. I'm going to focus for the demo on an example use case. I'm going to look at the 2018 Kilauea volcanic eruption and subsequent collapse. So this happened, there's a major event on April 30th, 2018, the summit collapse of the volcano. That eruption continued through September, and during that time period, the crater went from 280 feet to 1,600 feet deep. Its diameter more than doubled. There was 700 dwellings destroyed by the lava, 30 miles of road covered. It was a very big event for, especially for Hawaii. And so if we want to kind of look at and see what was happening here, we can go to our search form, search.asf.alaska.edu. And when we get there, we'll need to log in. If it's the first time you've logged in, you can create a new Earthdata login account. And that Earthdata login is free. You just have to say kind of what your area of research is or your area of interest. I always put cryosphere because I have a background in glaciology. And it will prompt you to accept the ASF terms and conditions, or the data access conditions, the EULA. And the text is available on our website in addition to, you'll be able to see it and read it when you log in. When we get there, there's a lot of really good resources in that upper right hamburger menu. I'll show those as well. I just want to highlight them before we get into the demo. The video tutorials, there's really great video tutorials that the discovery team has put together on searching with Vertex, but there's also one specifically for on-demand processing, which is what I'm going to go through today. They have a user's guide at docs.asf.alaska.edu, and we have a user's guide for the on-demand processing software, which we call Hype, and all of the on-demand processing stuff is covered in those documentation. There's 3 sections on using Vertex, our SDK, so you can do programmatic, or if you wanted to, you could hit the API directly. And Heidi has also put together really great InSAR and RTC story maps that walk you through the whole process in a very nice visual way, as well as some other information on our products and what is SAR and other tools that we provide. So I'm going to hop over to Vertex for a demo now. So I'm going to go to search.asf.alaska.edu. That'll bring up the Vertex front page. I will want to sign in the upper right here. That will pop up the Earthdata login. If you haven't had an Earthdata login before, you can register. Or if you have one, you can log in. You get the right account. Automatically redirect you back to Vertex. So my account is logged in. So I want to look at Hawaii. So I'm going to zoom in here on Hawaii. And I'm in a geographic search for Sentinel-1 data by default. That's what I want right now. But there's a variety of other data and different ways to search, which I'll cover the baseline and SBAS and on-demand product search in this webinar. So I want to look at this volcano right here. So I could draw a area of interest, kind of bring the area of impact by the volcano if I wanted to, or I could drop a pin right where the volcanic crater is, which will be sufficient for kind of what I want to look at now, which is this area. So I'm going to go ahead and just stick with the pin. I know the event happened on April 30th, 2018. So I'm going to search kind of plus or minus 12 days from April 30th so that I can make sure that I get an accurate, like the pass from Sentinel A and Sentinel B over there and kind of see the range of data around that event. So April 30th there, back 12 days to the 18th. 2018, April 30th, but I want to go forward to the 12th. It's 12 days after. So that gives me a kind of range of what's happening around that event. I may want to pop open the additional filters here because I want to produce interferograms. I know that I need to select specifically single look complex because it has the phase data in it. So I'm going to filter by single look complexes. When we're doing on-demand processing, we currently only support the IW beam mode, which the vast majority of acquisitions over land are that. So I'm just going to go ahead and filter that out. And I think I only want the ascending satellite scenes. I can search for either the satellite going kind of ascending or descending or having both. But I know that the look view is going to be pretty good from the ascending satellites here. And I'm going to go ahead and click search. Right before click search, it kind of gives me info on how many files it's going to be found even before I click search. So there's only 3 scenes now that meet all these criteria. If I do ascending and descending, I'll get 7 files. So this is just to kind of fill down and get right to a good view. So it'll take just a second. So our scenes we popped up, there's one from April 20th right before the event, and May 2nd and May 8th right after the event. I'm going to go ahead and start with the April 20th one. So I've got a reference scene, kind of the scene right in the area right next to it. If I only wanted to look at one pair and I wanted to pick a really good pair, I may highlight that reference scene and hop over to the baseline by clicking the baseline button in that center info panel. That'll switch us to a baseline search, which you can see up in the search type in the upper left. And it has that scene name dropped into the search criteria. So you could go straight here if you already know the scene name you're interested in. That pulls up this kind of baseline search criteria, or this baseline search. Based on that reference scene, people found 387 other scenes that would work as InSAR pairs. But we may want to filter quite a bit down to a really good pair. So I only want one that brackets that event. So I want to go forward in time because I started before the event on April 20th. So I want to go forward in time. So I'm really only interested in this side. And the tighter the perpendicular baseline, the better the InSAR pair typically. So here's the closest forward in time perpendicular baseline pair. I highlight that. We got a really nice 12-day pair covering that event with 8 meters of separation between the satellite when it took the event, or it took the first acquisition and the second acquisition. So that's a good InSAR pair. I'm going to add that pair to our on-demand processing by clicking the on-demand button next to the pair. And I can go up to the on-demand queue up here. So this is how I would submit a job. So I've got my pair here. I can adjust quite a bit of customization options. Each option has some text about what the option is and what's happening with it. So I can adjust the number of range and azimuth looks from 20x4 to 10x2. That'll change the product resolution from 80 meters to 40 meters. I can include the DIM file that was used for processing, some incident angle maps and look vectors and displacement. I'm just going to go ahead and include everything in the product package to have a good look at it. So I'm going to click the Submit One Job button. This gives me the opportunity to name the job, and it gives you a drop down of previous names. I could add this pair to a project that I've already done by giving it the same name, Then when I go back and search later, you'll be able to pull that and all the other pairs associated with the product. I'm going to give this one a new one so I could get straight to it. I'm going to call this Hawaii. I'm just going to call this Hawaii demo. I'm going to submit that. So we get the view that jobs were submitted and this little toast pop-up. I can click on it and it'll bring me over to the on-demand search type, which you can also go straight to in this menu and kind of look for your products. I can filter then by that product name. There's my Hawaii demo. There's the one pair I submitted. You can see it's pending, so we've submitted it. It's waiting to spin up a machine in the cloud and start the processing. You get information on the two pairs that were used to create that product, as well as all of the information associated with that product. Now, I went ahead and ran the baseline demo pair ahead of time so we can see what it looks like when they're done. So switch to previous project, that's the same pair right here. When it's done, you can click on it and it switches from the status to an actual view where you can view the output product. You can add that scene to download to your download queue. It still has all of the information available with it, and specifically it adds when the product expires. So you make the products available to you for 14 days. After 14 days, they expire and are deleted, but all of this information will still show up so that you can resubmit the same thing later if you happen to lose it or didn't download it in time. So I'm going to go ahead and instead of adding it to my download queue, I'm just going to directly download the file. Let's see, it's downloading there. If I wanted to look at this pair, when done downloading, I would zip the archive and I might load the geodes that we produce or that we distribute into ArcGIS or QGIS, which I've done here. So we'd see above Hawaii, we can load in our interferograms. So that covers the whole thing. You see you don't get very good coherence and data over the ocean, but you can see some really nice interferogram pattern right over the volcano. So everything that we distribute is cloud optimized. It has metadata files associated with it, ready to go for GIS applications. And if I could get, if you click the view metadata, it will load. ArcGIS is very slow on this machine for me. You get this really nice documentation of the product, the reference scene, the secondary scenes, when it was processed, some information about the products and the product you're viewing specifically, credits and how to tell people how you've used the data, where you got the data from, all of those kind of things. So I'm going to hop back over to Vertex. Now we've got this reference scene that we found. And I showed the baseline search, the reference scenes. Remember, Vertex remembers the last reference scene you used, so it's still there. If I wanted to do a time series of the volcano instead of just looking at the one event, since I know it went through September and there was some buildup starting in January, I might actually want to develop a time series. So I can take that reference scene and instead use it in the SBAS tool. So the SBAS tool is right here, or you can get to it in the search type. So I'm going to hop over to the short baseline subset using that reference scene. This takes a little bit of time because it's still a time series stack of all of the possible pair combinations back in time using that scene as a reference scene. So when the search results come up, there's 3,600 pairs that are possible in this time series. You get information on each pair as you click through about the two acquisition scenes, and they highlight in the kind of this pair menu what they are. So this one's pretty dense. I zoom in a little bit just so you can see kind of that pair network that it creates. Then you can click one and it'll highlight the scenes up here and in your menu. So I said before that I wanted to look at just January. So this is all time that it initially pops up. So I'm going to do 2018 January to filter out results. I'm just going to start at the beginning of the year. And I know the event sort of ended in September, so I'm going to go 2018 to October 1st, just to build a time series of that event. So that brings us down to 287 pairs. That's still quite a bit of data to process. There's some pretty big perpendicular baselines in there. I'm going to make sure I restrict it to just 150 meters, which seems to be a really good cutoff for InSAR, at least to start. And I only want pair for 12-day, up to 12-day separation between scenes, just get a really tight temporal baseline as well when I'm processing. So I'm going to kind of move the slider around. And so that filters this down to this really nice time series of 81 pairs. And I can actually add a custom pair. I want to see kind of the whole event on, so I may also add a pair that covers the entire time series. So you can just add pairs in and remove them if you don't want them. And there's a chance this might not give us a good product, but if it does, we can see kind of the whole event in one snapshot that way. So if I wanted to submit this time series for processing, instead of adding them pair by pair, I can click up here and add the entire pair list that's generated here for SAR processing. Go back up to my on-demand queue. So there's 82 pairs now in my queue. I've processed some this month already, so I have 916 kind of jobs I can ask for, or InSAR or RT products I can ask for left this month, so I have plenty of space still. We give you 1,000 per month by default. It remembers my options from last time, so I don't have to select again. And I can, to get a good view on kind of the pair list once it gets kind of large, like this one is, I can change on how the data is sorted just to give a good view, where I'm looking at the oldest scenes first and based on when I added them to the queue. So I'm happy with this stack. I'm going to submit all 82 jobs for processing. So I'm going to call this Hawaii stack so I can see the stack later. And I double check that I'm submitting InSAR Gamma jobs with the stack. Submit them for processing. You'll see your queue kind of tick down as it submits them. So they're all submitted. I can click the toast to hop over to my on-demand search, or just go to on-demand search directly. So you'll see I've got, this is all of my products, 166 products I've requested now total. All those ones I just submitted are pending, and all the ones I had requested before are in there. I want to filter to our stack that we just submitted. And you can see there's now 82, those that we just submitted. They're all pending. They'll kick over to running very soon. And in about 45 minutes, they should all be done. We can typically process 400 in parallel. So we can get you a stack very quickly, 45 minutes to an hour. Now that that stack is submitted, I might sit around and wait for it to finish, or I've got an example of that same stack, the same 82 products that I submitted earlier, so you can see, and they're all filtered and searched here. I can zoom to any particular pair I'm interested in, still get all the details and how they were submitted. And instead of downloading them one by one, I could add them to the download queue, or I can add the entire stack to the download queue. What you see here is there's 82 products, but 78 files to download. That's because some jobs will fail. And when they do, you'll get a notice that they failed. And you can see which pairs failed directly. These ones are failing because the geometry of the scenes, as reported in the metadata, is actually the overall bounding box of the scene. So when you generate pairs that overlap, sometimes they don't actually have overlapping data. What's overlapping is just the no data bounding box. So that's what happened in these ones. The processing will fail as we go. You don't need to worry about those. They weren't good pairs to begin with. And we're working on filtering those out. Hopefully this week that will land. So I'm going to add my 78 jobs to the download queue. That brings me the ability to kind of copy the URLs to all the files. So I could copy paste it into a text file and use wget or curl or aria or any of these downloading methods a lot of people are comfortable with. I can also download a bulk Python download script. So if you have Python on your computer, it will automatically download all of them for you. Windows will warn me because I can run stuff with it. I'm going to click go ahead, keep it, and download it. And I'm going to open this script. And it's a Python file that you can just run, just type, in your terminal or interpreter, just run the script. But it includes all of the links to all the files right here, and we'll loop through and download them all for you. There is some information on how to use the script right in the top. If you need a reminder, it's not exactly how to use it. And if you have something that supports a metalink file, you can tend to download the metalink files and other things to help you download the data. So at that point, I've got a Python script. I can download all the data. I've got now 82 analysis-ready products that I can use MintPy or GMT to build a nice time series analysis of my kind of InSAR stack over Volcano. At this point, I'm going to switch back to my presentation. So that's kind of how you would do everything in a very nice graphical interface. If you're working on large workflows, you often want to programmatically do these kind of operations. So there's 2 Python packages we at ASF have produced to help you with this kind of thing. There is an ASF search Python package, and it's a basic search and download package that's being rapidly developed. It's intended to feel just like Vertex. You use it just the same way. I've got an example of doing InSAR pair picking for the exact same search that we just did. So I import ASF search. I can do a geographic search like we did in the demo. I can select the platform to be Sentinel-1, the processing level SLCs because we want the phase data, beam mode IW so it's compatible with on-demand processing. I can intersect and all the scenes that intersect with any valid WKT string. So this is a point, and this is the volcanic crater. And if you remember in Vertex, when we did our geographic search, anytime I do a geographic search, you can actually copy paste the WKT string out of Vertex. So I delete my kind of point that I dropped. I draw my funny bounding box over the area I'm interested in. It actually puts that WKT string here, so you could copy it out and use it for programmatic workflows. Vertex is actually a really good place to build these strings, but you can convert any Shapely or GDAL Ogre polygon to WKT very well easily, or any shape file. And so same filter from 12 days before the event to 12 days after. That gives me a bunch of search results. If I wanted to, I could download those results into a data directory just directly by saying search results.download. You'll need to provide an EDL token currently. More authentication methods to log into Earthdata login are coming. So this is likely to change and be a lot easier soon. Once you've got search results, you can also just from Python request on-demand processing of those scenes. So I'm going to import our Hype SDK, it's our on-demand processing software development kit that allows you to kind of search and submit for these jobs, or submit these jobs for processing and then download them later. So log into Hype, it uses the same Earthdata login as Vertex does. This will prompt you, ask you for your login. So you'll type in your username and password. And then I'm going to submit a bunch of jobs we tend to call a batch, so we provide a helper class for that. So for every scene that we found or granule in our search results, I want to get the 2 nearest neighbors. So the 12-day or the 6-day and 12-day pairs. And for all those neighbors for each scene, I'm just going to submit an InSAR job for them, and I'm going to call them Hawaii pairs. When I do that, those will also show up in Vertex just the same. Vertex looks at the on-demand database, and you can view them in the on-demand kind of search results. You'll see them as soon as you submit them. From the command line or from the Python interpreter, you can also just use Hype to watch the jobs. This will give you a nice like progress bar that says, you know, these many jobs have been submitted. This is how many have finished. And then when it's done, kind of return you all the updated job information, which has the download URLs and everything. And you can just directly download it to a data directory. So everything that you saw me straight in Vertex can also be done programmatically. You can really leverage this to watch a specific area over time. If an event's happening now, you can set up kind of a repeated search that will go through and find the new stuff, submit that for processing, and you can build your time series forward into time. And I want to show, I think I have 2 minutes, so I want to show one more thing. Need to move this, here we go. Okay, so I'm going to go to a new tab, and I'm going to go straight to our documentation, which is hype.docs.asf.alaska.edu. Can't remember where that is. You can also go to Vertex and just go to the Hype Users Guide. So Hype is the on-demand processor. That will pop up into Hype Docs. What's really nice about our documentation is that we have this section on using. If you click on the Vertex link, it will pop you back to Vertex to their video tutorial using it. So you can kind of watch a tutorial they put together on how to go through it. We have documentation on our SDK. There's an API reference, so everything that every method and everything is well documented, doc strings and examples. We also provide an example Jupyter notebook, which you can see here. It kind of walks you through kind of 3 use cases, which is submitting RTC jobs, submitting InSAR jobs, which I just showed sort of how that works before with a little code snippet, and also submitting auto-riff jobs, which is glacial ice feature tracking and give you an ice velocity map. And then discusses monitoring jobs and downloading files. What's really nice about this Jupyter notebook is that you can launch it on Binder. When you do that, let me get over to it. You click this link, it'll pop you into a mybinder.org view of it, and it's actually an interactive notebook. It's got everything you need already pre-installed. You can import Hype SDK. You can authenticate to the API. I said this a little bit ago, so my kernel has died before the webinar. So I won't actually demonstrate doing much in here, but it is an interactive notebook that you can use and run through and do all of these. This will give you an initial set of kind of things to look at in Vertex and the on-demand queue that are just nice examples. So I highly recommend checking out our documentation as well. And on that note, I'm going to put up some contacts and resources. There's a bunch of resources for Earthdata itself, all of NASA's data or Earth observing data, how to learn about it, get access to it. ASF has our main website is pretty rich and has a lot of good information there. We also have a user support office and science consultants that could help answer your questions. Vertex has its own user's guide, just like Hype does as well. And in Hype, the part I work on mostly, also has a Twitter that you can follow to get new updates on new processing options that are available, changes to our software, updates to the SDK. We have a Git channel that if you have a GitHub or Twitter login, you can just hop in and chat with us, the team, directly, and we can help answer your questions if they don't feel like big questions you'd want to email or open an issue for, just quick chat questions. You can also find us on GitHub. All of our software is open source, VST3 licensed. If you encounter problems, you're welcome to open issues on that software as well. And as always, you can email me at jhkennedy@alaska.edu. I'm happy to answer questions as well and help people along. So at this point, I can toss it back over to Jennifer and we can open it up for questions.